A solid cylinder of mass m and radius r is set in rotation about its axis with an angular velocity omega naught. Suppose this is the solid cylinder. Initially, it was rotating clockwise with angular speed omega naught. Now it is gently put over rough horizontal surface. As soon as it comes in contact with the rough horizontal surface, the lowest point of the solid cylinder has linear velocity in the leftward direction, and that is equal to r omega naught. So it will experience friction force in the rightward direction because friction opposes the relative motion. So it will experience friction force in the rightward direction. As a result, it will experience opposing torque. So its angular velocity will decrease, and at the same time it is experiencing force in the rightward direction, which is a friction force. So it will accelerate linearly in the rightward direction. So let's apply Newton's second law in both translational motion and rotational motion. So we will have F is equal to ma. Now since it will slide over the rough surface for some time, so the friction acting will be kinetic. So we will have mu mg is equal to ma. So acceleration in the rightward direction is equal to mu g. Torque is equal to I alpha, and torque is also equal to force into perpendicular distance mu mg into r. Moment of inertia of the solid cylinder is mr square by 2. So we are having alpha is equal to 2 mu g r divided by r square. So that is equal to 2 mu g by r, and this is retardation. It will reduce the angular velocity. Let's apply kinematical equations for the translational motion. So we have v is equal to u plus at, that is v is equal to 0 plus mu g into t, where t is the time duration during which it will slide. Once sliding is finished, it will perform pure rolling. Now the kinematical equation for rotational motion, omega is equal to omega naught plus alpha t. So omega is equal to omega naught minus 2 mu g by r into t. We have taken the negative sign for alpha because it is retardation, angular retardation. Now after time t, they will perform pure rolling. So we can use v is equal to r omega. So we have mu gt is equal to r into omega naught minus 2 mu gt divided by r, or mu gt is equal to r omega naught minus 2 mu gt. 3 mu gt is equal to r omega naught. So t is equal to r omega naught by 3 mu g. So this is the time duration of sliding motion. So the linear velocity after sliding motion is finished. We have v is equal to mu g into t, which is r omega naught by 3 mu g. So r omega naught by 3. And the angular velocity after the sliding motion has stopped. We have omega is equal to omega naught minus 2 by r into mu gt, which is r omega naught by 3. So angular velocity is equal to omega naught by 3. Let us calculate the total kinetic energy of the solid cylinder when it is performing pure rolling. We can write it as Ke2, that is equal to translational kinetic energy, which is half mv square, plus rotational kinetic energy, which is half I omega square. So we have half m into v square, which is r square omega naught square by 9, plus half I, which is mr square by 2, into omega square, which is omega naught square by 9. So by adding these two, we will get mr square omega naught square by 2 into 9 is taken out in the bracket 1 plus 1 by 2, which is equal to mr square omega naught square by 2 into 9 whole multiplied by 3 by 2. So that is equal to mr square omega naught square whole divided by 4 into 3, which is 12. So this is the final kinetic energy, and initial kinetic energy of the cylinder is half I omega naught square, half into mr square by 2 into omega naught square. So the loss of kinetic energy is equal to initial minus final is equal to mr square omega naught square by 4 taken out as common in the bracket 1 minus 1 by 3, which is 2 by 3. So 2 by 3 into 1 by 4 into mr square omega naught square. So that is equal to 1 by 6 mr square omega naught square. So this is the loss of kinetic energy due to friction, and that is our answer.